Hello students, in this class we'll solve examples based on Euler's equation. So here examples are finding a extremal function for the given functional. Okay. So using Euler's equation, so we'll get the solution. Every solution of the Euler's equation which satisfies the boundary conditions is called extremal or a stationary function of the problem. Okay. So the extremal can be obtained easily in the following cases. Okay, in the different cases based on the given function f. So when f is a given function in the given functional. Okay. So this f is independent of x, then f minus y dash into partial derivative of f upon partial derivative with respect to y dash equal to 0 gives the solution. So means just we have to substitute f and differentiate with respect to y dash, then substituting here and we will get the required solution. So second case is f is independent of y, then this equation gives the solution. When f is independent of y dash, this direct partial derivative f with respect to y gives the solution. When f is independent of both x and y, then y double dash 0 is equal to 0 gives the solution in the form of y is equal to ax plus b. So this is a straight line solution. So these are the different cases for which so we can get the required extremal for any given f. Based on f, so we'll get the solution. Now we'll have some example. Okay. So find the extremal of the functional given integration from x1 to x2 of y dash plus x square y dash square dx. Okay. So for any given such function, we have to note on what is f. F is the function which is inside the integration. So here f is y dash plus x square plus y dash whole square. Okay. So we can observe this function as per the different cases as we have discussed above. So here this f is independent of y. So when f is independent y, so this equation gives the solution. So now this equation gives the solution. So to get the solution, we have to differentiate given f with respect to y dash, and after that we have to differentiate ordinary with respect to x. Okay. So now using this equation, so partial derivative of f with respect to y dash is equal to some constant. This implies so differentiating this f with respect to y dash. So y dash is 1, then x square is constant because it's partial differentiation, so y dash square. So with respect to y dash means 2y dash. So the partial derivative is this is equal to some constant. Then simplifying this for y dash, it is equal to y dash equal to c minus 1 upon 2x square. Okay. Y dash is nothing but dy by dx. So it will be dy is equal to multiplying dx to this constant expression. Okay. Now we have dy is equal to, but our aim is to get what is y function. So from this dy, integration gives y. Okay, integration of dy is equal to, this is constant, integration of 1 by x square dx. So integration of dy is y, this constant you take as an c1, so it is c1. Then integration of 1 by x square is minus 1 by x square. So plus another constant of integration. Therefore y is equal to minus c1 upon x plus c2 is the required solution. Okay. So here for the given functional, we observed the function type, then we got it is independent of y, so we used this equation. So in general, always for any function, if you are not worrying about the function type, directly we can apply Euler's equation. So let us have one example based on that. So find the extremal of the functional. So from integration from x0 to x1, y dash square upon x cube dx. Okay. So we need not to bother whether what type of this function. So just directly we can apply Euler's formula, Euler's equation. Okay. Here f is y dash square upon x cube. So Euler's equation is, we know this is the Euler's equation. So for finding extremal of any given functional, directly always you can try with Euler's equation. Okay. So we need not to bother to f is of what type, whether independent of y or x or y dash or simply x and y. So directly we can apply this Euler's equation. Okay. So partial derivative of with respect to y is, there is no x, no y, so it is 0. Then this d upon dx partial derivative with respect to y dash. Y dash is, denominator is constant, y dash square is 2y dash. Okay, so 2 times y dash upon x cube is the partial derivative. Then once again differentiating with respect to x this. Okay, so by applying u by v rule, because y dash is a function of x, so we are differentiating with respect to x. Okay, so by applying u by v rule, this is the derivative of 2 times y dash upon x cube. Okay, so then once again, so simplifying this denominator going to 0, so it is x square y, x square, this 3, then x into y double minus 3y dash equal to 0. Then this simplification, product is 0 means both may be 0 or any one is must be 0. So we taking this x y double dash minus 3y dash is equal to 0. This gives x y double dash is equal to 3y dash. Okay, so then y double dash divided by y dash is 3 by x. Now integration of this. So one of the rule of integration, if numerator is derivative of denominator, so integration gives log of denominator. So using that idea, so it is log of y dash is equal to right hand side 3 times log x and constant of integration log c. So now applying law of logarithm, it is y dash is equal to x cube c. Then y dash is again dy by dx, so taking into variable separable form and integrating with respect to separately x and y. dy integration gives y, then cx cube with respect to x is cx raised to 4 upon 4 plus constant of integration c1. Therefore we have y is equal to c2x raised to 4 plus c1. So here this is the required extremal of the given function. This itself is the solution of given problem. So like that you can solve any such examples, and I have done some other examples in the regular class, so you can also try all other homework given, and also you can have some other examples to solve this. Okay, thank you.